Have a few. Have a few.
You definitely want one.
Yeah, trust me.
And in order to trigger the event, you can just call delete.
I don't really expect myself to understand.
Oh my god.
Just do the share thing, dude. It should just work.
I can't do it.
Oh, update. It's not always.
Just update it. Take 2 seconds.
Wait.
Well, it's probably the sort of thing where you have to update like at least once every few months.
You reckon the Max would be a person that never upgrades his software?
You know,
Aren't they?
yeah, actually. What the fuck happened?
In the morning there was misunderstanding. Now I mean it.
It's in my downloads. It is query results.
Plus 25. It's
So
expansion.
you feel this is 6 months for?
Minus 10 aggressive.
Prestige.
Just kick it off on Monday. Fucking
Nice present, mate.
Thank you. Awesome.
Come on.
Big Max is watching.
Okay.
Inputs. Is there like an API for this or something?
So, can everyone see what's going on here? Sweet. Okay. Let's begin. So this is extract of the talk that I actually gave yesterday, and it's kind of talking about parser combinators. So I want to just show something that would. Give me a second. So this is a regex.
Pass it.
Yeah, give me a second. So here's a regex that matches valid emails. Now, as you can see, it's a bit of a notorious hellscape. No one really likes writing regexes because they suck. Is there a way to make that the main screen as well? Okay, it's just weird seeing me talk. So no. Yeah. Okay,
Oh,
cool.
okay.
So, regexes are a kind of notorious hellscape, but we have parser combinators. So parser combinators, in the talk that I gave yesterday, I immediately showed parser combinators because they depend on applicative. And I thought they were a really good demo of how applicatives can be used to build some kind of really cool structure. So, at their core, what do parser combinators depend on? First of all, they kind of depend on this alternative type class. And alternative is quote unquote a monoid on applicative functors. And so you have to define two separate members of this type class. You have the empty, which is what is regarded as the failure. We're going to get to what that constitutes later on. Yep.
Is that the same as the monoid empty?
Yes. No, not quite. No, it's not the same as the monoid empty. It's a little bit like the monoid empty. Yeah. Yes, it's the same. Sorry, it's the same as the monoid fail. So this empty on alternative should be fail. Monoid fail. Okay. And then we have this combine operation where what we can do is based on the F, we can define the custom implementation that chooses either some PA or some QA and yields it. So here's me setting up some useful helpers for how the alternative type class works. First of all is this one, what's called many. And what it's going to do is it's going to repeat it. Many calls out, as you can see, many calls out to some, where some will, it's going to repeatedly apply. Sorry, my words aren't working. In both of these cases, both many and some will repeatedly apply this weird alternative thing to some V. So it will be V alternative. And at some point in time, one of those alternatives will fail and that alternative chain will stop happening. So it's gonna repeatedly apply it. Critically, you'll notice that this V is lazy such that we don't get some sort of immediate stack overflow as it recursively applies itself until some sort of failure point. Here's some alternative syntax, blah, 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 blah. And so here we get to the actual core of what the parser combinator is. So some parser of some type A takes some input stream, and what it will do is will yield multiple values, where those values are the things that you're passing, associated with some input stream that has been consumed in some sort of way. So if anyone's done a compiler's course of some description, if anyone's written left to right parser, this is the dot moving along the input stream for example a pushdown parser of some description. And when we run the parser itself, we take that input stream and we cram it in. If we have a list where the head of the value has an input stream that has not been fully consumed, we get very upset. If we have multiple values that we've somehow passed, given some input stream, that's definitely incorrect. We've created a parser combinator that has passed an ambiguous grammar of some description. That's definitely not correct. But if somehow we spit out some sort of value of some arbitrary type A and we have a completely passed input stream, we spit out that value. We spit out the result that we have passed. So the most simple parser is one that passes a single character. And given some sort of input stream, if the input stream is empty, we say we pass nothing. If it has something, we pop out the head and we move the cursor further down the stack. And then we say we've passed one thing, one candidate, which is this character. So we can also define our functors, applicatives, and monad instances for it. For functor, we pass the input stream, we fetch out every possible candidate and their respective remaining streams, and we map over the values. For apply, what we do is we first of all pass some of the input stream into the F to extract out the function. We pass in the rest of the remaining stream to extract out the value, and then we apply both of those, and then we hand back the stream. For monad, what we do is pretty much for every possible value that we have passed so far, remember that the parser, given an input stream, can pass multiple different values with multiple different remaining streams. We take each of those values and remaining streams, we take those values, pass them into the flatmap function, also providing the associated remaining stream associated with that value to yield some new parser, and then we hand that parser back. Everyone clear so far? Cool. So here's that failure that I told you before about. So in this case, failure is a parser that takes some input stream and passes nothing at all, yields nothing. We also have this combine operation. What it will do is it will take two parsers, it will feed both of the input streams to both of the passed values and then combine their pass with the things that they are passing. So now this parser is going to return it's going to try and pass two things at once. And it probably can. And here we have another one, which is option, which takes two parsers. It tries to pass the first one. And if that first one succeeds, we use the result of that parser. But if that doesn't succeed, it returns an empty list. It said, I failed. I didn't pass anything. It goes on to the next parser and passes the input stream to that one. And so we can then map those implementations onto what alternative is. So remember how I said alternative, it has an empty. Empty is failure. There's nothing. It's going to pass nothing at all. And this diamond is option. It's going to take some sort of, some first parser, it's going to pass an input stream into it, and if it fails, it's going to go QA. Which means that if you go empty, diamond, some other parser that may or may not, some other parser, we will always preference the some other parser. Because what option will do is it will parse it, we'll get an empty list, and we'll go, I'll take the other one. And also vice versa. And that's why it's called a monoid on applicative functor, is because the identity in terms of what this does is the failure case, which is empty. So with that, we can start to build up some simple functionality in terms of useful kind of utilities. First of all, the satisfy. We use this item parser that's going to pass out some char from the input stream. We flat map on it. We check whether it matches its predicate. If it is, we wrap it up with pure. Otherwise, we fail the parser. And let's keep going. One of just checks whether it's contained within some list of characters. Chain L. What it will do is it's a recursive function that it's going to take some parser of some operation that takes 3 separate values and some other value, some other parser of values that can be acted upon by that operation, and yields a parser of those kinds of values. We're going to see how that works in a second, but you can kind of see what we can do is we can use recursive operations to build parsers, we're going to see why that's kind of useful later on. I stole this off a friend. I don't know how it works. You can kind of, it will be quite cool. So here's some kind of funky ones. As you can see, char satisfies. If we want to pass some character, we can pass some character by using the satisfy combinator and saying, yeah, if it equals this character, pass it. Otherwise, fail. Spaces, what it will do is it will use this many combinator. So what this many combinator is expanding out to is one of alternative, one of alternative, one of alternative. Oh, sorry, I lied. No, I won't do that. It will actually. Yeah, we'll do that. Oh, sorry. It's using applicative, sorry. So what the applicative instance here was the one where it passed in the stream. Sorry. Let's go back to that. The applicative stream, what was the applicative? Yeah, applicative. Yeah, it takes the stream, passes it into the first value, and passes it to the next one, and the sum of the implementation up here is the one that is recursively applying this app over and over and over again. So we can understand that, oh Jesus, we can understand that this many is repeatedly applying this parser combinator over and over and over again until it says failure, and then it will spit out the list of characters that it's passed, and then we'll collect it into a big fat string. Alpha does effectively the same thing with letter and digit, and you can kind of see what's going on here. We build something that passes a string by progressively passing each character at a time, and then recursing this string combinator. We have one that does tokens, which is just, a combinator with spaces. We have reserve, which is a tokenized string, etc., etc. So you can kind of get the point. We can actually start to build useful functions up these from a very, very small base of utilities. So let's do something that we think is rather reasonable and useful, which is we're gonna try and pass some arithmetic. So here's the EVMF from arithmetic. I think this was stolen directly out of the Red Book. Oh, not the Red Book, the Dragon Book. And here we go. We can pretty much map it directly onto the actual parser combinator machinery that we've kind of seen.
Check if everyone's familiar with the EVMF.
Is everyone familiar with EVMF?
Yes.
Cool.
Yeah.
So we build some grammar, we build some evaluation function, pretty standard stuff. We build parsers that will consume the input stream and then map them into our expression grammar. And here you can see we've used this chain L1 function that's taking a parser of term and it's using this addop function. And what it's going to do, where addop is a parser of some sort of function that will consume two expressions and produce a new one, and it will use this infix operation function. What it will do is it will take some f, and provided that it can consume the token associated with that function, if it's, whether it's a plus or a minus, we can promote it into a parser context such that then we can preferentially, based on whether we've passed this plus or minus, yield the appropriate function. Critically, you'll notice that this chain is co-recursive. If you write a strict implementation of applicative, this will not work. It will Stack Overflow, because what it will do is it will try and evaluate, this factor will evaluate the expression, and we only want to evaluate the expression when this chain L function actually needs it. Remember when we're doing this chain L1, it's doing some many, and that many calls out to applicative, and we want to prevent that applicative from using the right-hand side when the parser on the left-hand side has succeeded. From using the right-hand side when the parser on the left-hand side has failed. And then finally, we can build the rest of them. We have some apply function, and it's just going to take the input stream, it's going to map the evaluation function over it, and then right at the end, we can use our calculator. Ta-da! There we go.
Is that what this work?
It actually works.
Calculator compiles that.
Making it sweet on time.
Also run the one.
Okay.
Also run.
Probably not. Hey, there we are. Awesome. Woo. So there it is. That's the satisfies all of operations. It's kind of a useful parser. It's kind of easily understood. We can actually refactor this out if we want. Preserves referential transparency. We're all fucking happy. Awesome. Now, so this is like the Mega Man section, and then the next section is kind of like to those who might be new to Scala. And so the next section is kind of evangelizing this as a replacement for regex. Now, there is a equivalence for regexes to parsers. Like anything we can do in a regex, we can do with a parser combinator.
The inverse is not true.
We'll get to that. So this is effectively a little test harness that I built so that people can play around with parser combinators in this file if they want to see how regexes work. So it's effectively taking some sort of string of candidates, and it's using both a regex and a parser to actually parse them, and it will tell you if that matches. So as an example, let's just go down. Oh, shit, sorry. Come up here, and then we parse them. So you can kind of see that this plus that we see in regex is equivalent to some. This star that we see in regexes is equivalent to the many. Come on. Jesus.
Also.
Yeah, I don't know why the class is. Yeah, here we go. As you can see, it's matching everything we expect it to. As you can see in the many case, it's matching the one with the empty string as well. We can use this kind of alternative operator to choose between A or B, and any of is your standard square brackets, and if we want, we can compose these equations together in fun ways. Ta-da! Cool. Equivalence. So pass HTML with a regex. Click the first Stack Overflow. Wait, you can't see this. Okay. I go to Stack Overflow and I'm like, man, I'd really love to pass some HTML with regex. And you get told that you can't pass a HTML with a regex. Why can't you pass a HTML with regex? And so you scroll down and you find out that HTML is a type 2 grammar and a regex only passes type 3 grammars. So you're like, okay, what the hell does that mean? So you go to your Chomsky hierarchy and you look at your Chomsky hierarchy and you think, oh my god, what the hell is going on? And you see that
That's why you go to uni.
that's why you go to uni. And so you look at your type 3 and you see it's a regular language and it can be passed with a finite state automaton. So when we write our regexes in most decent programming languages, the regexes get compiled to a finite state automaton. Technically a non-deterministic one initially, but then it finally gets to a finite state. And you can kind of see that we have production rules. We have the kind of languages, given a language of these forms, we can pass languages with a finite state automaton. And you can kind of see what the meaning of these symbols are. And here we have type 2, it's context free, it needs a non-deterministic push-down automaton. Now, I happen to know a certain language that is a type 2 context-free language. And it's this one right here. There you go. Some production S is either the string of AB, or it's A and some other S in the middle, and then B. So characters that will match that language are in L that we can generate from this grammar is AABB, AAABBB, AAABBB. So you can kind of see it's matching on both sides. Now, we were to think to ourselves, if we were to draw a finite state automata, we're building some graph that on each character we go to a different node in that graph. How many states do you need to match this regex? You need infinitely many, because you can have infinitely many A's on the left side. And so you're going through the input stream, you've consumed all your A's, and now you have to somehow remember how many B's you have to match. You can't do that. You need a push-down automata, or you need just a Turing machine or something. Cool. So, let's run part 2. And, oh, wait, I haven't done it yet. Did that work? Again, as you can see, here's our parser. Our parser is recursive. It's either a string of ABs or it's the character and then passing S again or B, and then when we actually pass it, we want to concat all those sub passes together. And right at the end, as you can see, here's it successfully passing those streams. But if we tried to write this pattern, we couldn't do it. It's against the laws of computer science. So that's cool. We can use parser combinators. One, we can do recursion, and that's the critical part. We've used this parser is able to pass itself, which is obviously Turing complete. And then the next bit is the fact that we have flat map, which means that we can also do context-sensitive grammars. I forgot to write the proof of that, but because we have flat map, it means that if we pass some A, we can make a decision on previous values that we've passed to choose some other thing. Unfortunately, a finite state automata cannot do that for an arbitrary A, which is sad. You can do that for some finite A. I don't know, like given, yeah, like maybe you've passed one thing and then you do something else, or maybe you pass one thing and you do something else. But if that A is possibly has infinite different values, then you need infinite states in your finite state. So, parser combinators, they're inherently more powerful than regexes and they're easier to read. Why would you not want to use them?
Not easier to read.
Definitely. I was trying to do JSON, but I didn't get around to it. So,
I like regular expressions. Like, I get it. They get unwieldy.
There's
Yeah, there's quite early.
cool.
And then Pascal helps I did.
Yeah.
This parser stuff like this. And
Yeah.
that's Jason.
Any questions?
Didn't you build a JSON parser?
That's the course. Feel free to steal implementations.
Cool. Awesome.
So build those JSON parser
Um,
on the fly.
Yeah, do it.
uh,
There's only 5 things. Come on.
I've already tried. It's painful. I don't like it. Yeah, that concludes this this section. Any questions?
What did you present it to?
James and some other guy and a few other people on Zoom.
The thing is, though, it's recorded, so people do actually go back and watch them.
Yeah.
We've seen Andy go back and watch Max's talks, so I'm sure there's other people that will see them.
Andy's been pretty diligent at watching the talks. And I've seen him rewinding and checking stuff again.
Yeah, cool. Now, does any I have some backup time in the last 20 minutes. I did a section on like the structure of how a free monad works under the hood. Does anyone want to see that? No one? Anyone? Maybe? Or do we all know?
I can see it.
How long do we have? We've got 25 minutes. Yeah, probably do that.
What was the alternative?
We drink, I guess.
Yeah, that's it.
Have a beer.
Carrot liqueur.
Quiet.
Carrot liqueur. Yeah, let's do carrot liqueur.
Speaking of beer, Joe's gonna be here soon.
Yeah,
Alright, Max, well done.
Hey,
that was good.
Yeah, it's kind of
Do you
interesting.
recommend to write your own parser combinator library or use the existing one?
use fast pass.
What was the name?
Fast pass?
We use parboil in our
Parboil
code.
actually quite good.
Like, it's already there. Just use it.
I didn't mean it. No.
Oh,
I-
We
I-
also
I-
use
that was a question that was
standard
answered. Don't use your own.
sorry?
I am-
We're also using the standard loop combinators.
Yeah.